Substances, pure matter. Although the chemistry of the real world is mostly the chemistry of mixtures, all matter is composed of substances. Dig a hole, buy something at a grocery store, pick an apple from a tree, or take a deep breath. The stuff you dig, buy, pick, or inhale is a mixture. However, the behavior of mixtures is based on the composition, structure, and behavior of the pure substances that compose them. Figure 115 summarizes the classification of matter from a chemical point of view. Elements, the building blocks. If you classify an unknown piece of matter as a pure substance, it means that the matter is made of only one substance. But there are two types of pure substances illustrated in Figure 115. One type of pure substance can be broken down into simpler substances. This type of substance is called a compound. Another type of substance cannot be broken down into simpler substances. Such a substance is called an element. Elements are the simplest form of matter. Figure 116 shows two examples of elements. Millions of substances are known to chemists, but only 117 are elements. These 117 elements combine with each other to form all the millions of known compounds. That's why elements are often referred to as the building blocks of matter. All the substances of the universe are elements, compounds formed from elements, or mixtures of elements and compounds. Of the 117 known elements, only about 92 occur naturally on Earth. Copper, oxygen, and gold are examples of naturally occurring elements. The remainder are synthesized, usually in barely detectable amounts, in high-energy nuclear experiments. Less than half of the 92 naturally occurring elements are abundant enough to play a significant role in the chemistry of everyday stuff. The fact that most matter is composed of a relatively small number of building blocks simplifies the puzzle of matter. However, the observation that such a small number of pieces creates such a variety of compounds means that the elements must connect to each other in countless ways. Organizing the elements. Your classroom might have a large chart labeled the periodic table of the elements hanging on the wall. This table is the tool you will use most in your chemistry course. A similar table is printed on pages 92 and 93 of this book, as well as inside the back cover. The periodic table organizes elements in a way that provides a wealth of chemical information, much more than you will notice right now. All of the named elements on the periodic table are represented by a 1- or 2-letter symbol. As Figure 117 indicates, these chemical symbols are a universal shorthand that is used to make chemistry communication understandable around the world. Just as it is easier and quicker for you to write USA instead of United States of America, it is easier to write AL instead of the word aluminum. As you can see, the symbol for aluminum is taken directly from the element's name, but some elements have symbols that don't correspond to their English names. Their symbols usually correspond to their names in Latin. Some examples are shown in Table 1-2. Compounds. You've learned that a compound is a pure substance that can be broken down into elements. A more complete definition is that a compound is a chemical combination of two or more different elements joined together in a fixed proportion. For example, water is always 11.2% hydrogen and 88.8% oxygen by mass. It doesn't matter whether a sample comes from a faucet, an iceberg, a river, or a rain puddle. Once you isolate the water from other substances in the sample, you will find that every sample of water is made up of exactly the same proportion of hydrogen and oxygen. Every compound has its own fixed composition, and that composition results in a unique set of chemical and physical properties. The properties of the compound are different from the properties of the elements that compose the compound, as shown in Figure 118. More than 10 million compounds are known, and the number keeps growing. Some common compounds are listed in Table 1.3. New compounds are discovered and isolated from natural chemical sources, such as plants and colonies of bacteria. Compounds are also synthesized in laboratories, where they are tested for a variety of uses ranging from medicine to manufacturing. Because the supply of useful chemicals from natural sources is often limited, chemists work to synthesize these compounds in the laboratory. The effort to synthesize Taxol, an anti-cancer compound found in the bark of the Pacific yew tree, is an example of how nature often provides the lead in compound synthesis. If Taxol can be made in the laboratory, then chemical engineers will try to find a way to produce it on an industrial scale. Formulas of compounds. The second column in Table 1.3 gives the chemical formulas for the compounds listed. A chemical formula is a combination of the chemical symbols that show what elements make up a compound and the number of atoms of each element. For example, the chemical formula of the compound sucrose is C12H22O11. The formula tells you in a compact way that sucrose contains carbon, hydrogen, and oxygen. It also tells you that the smallest unit of sucrose, a molecule, contains 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. Figure 119 shows a submicroscopic view of sucrose. Formulas provide a shorthand way of describing a submicroscopic view of the compound. In later chapters, you'll learn more about compounds and why elements combine to form compounds. You'll also learn how to determine the formulas for many compounds.